All right, let's pick up where we left off the last time, which was learning about valence bond theory and the hybridization portion of that. I mentioned a couple things in that video that are also part of the valence bond theory. That's the sigma and pi bonding. And I told you I'd come back and talk more about that later, and here we are. On the screen, you see a slide from the previous discussion. I want to revisit this particular slide and pick up kind of where I mentioned sigma and pi. We had just talked about the formation of hybrid bonds, and I pointed out that in this picture here we have sp2 hybridization. I hope you can pick that out because there's one, there's two, and there's three of them. So that's sp2. And then this blue part here, even though it's labeled, I'll do it again, is an unhybridized p orbital. And so we talked about in the previous video how we could have a sigma bond, which is a covalent bond formed between, in this case, two carbon atoms. They overlap. And then eventually these PZs from each of these carbon atoms will overlap themselves in a side-to-side fashion, and then these unhybridized P's will form the extra bond, the multiple bond, number 2 in a double bond, or number 2 and 3 in a triple bond. This particular example is just a double bond that forms as a result. So here we would have 1, 2, 1, 2, 3, 4, 5 sigma bonds form, and then after those 1, 2, 3, 4, 5 sigmas form, then we get a little overlap here from our unhybridized P to form the singular pi bond in this. Okay, so this particular molecule, the formula for this compound is C2H4. That's ethene or ethylene. There are 5 sigmas, 5 sigma bonds, and then the 1 pi. Okay, we're going to do some practice at the end of this particular video. But let's talk more about this sigma pi difference here. So here I've got a picture that kind of takes away all the superfluous stuff, and it looks at just 1 sigma and 1 pi forming between these two atoms. So when you bring two atoms together to bond, the initial connection that's always made first is the sigma. Okay, so here we get a sigma bond that connects those two atoms. Here, sigma bonds, I've told you, are end-to-end overlaps. So they come in head-on collisions, linearly, end-to-end. And these connections can be between either two hybrids, and that's what we have here, where this carbon has a hybrid orbital, this carbon has a hybrid orbital, and they're going to overlap. Or you can have a hybrid and a non-hybrid overlap. So let's go back to the first slide. And that's what we have right here, for example. We have a hybrid and a non-hybridized overlap. End to end, linear kind of a butting up, and that forms a sigma. Now sigmas then are always the initial connection. They're the important ones. They're the initial. They bring everything together. Sigma bonds are fairly strong. And they're difficult to break, but you can typically rotate, like just spin around the axis. They are that flexible. But the main idea here is that sigma bonds are first. They are the initial connectors. Now, in this diagram, what I really like about this diagram is that it shows you a couple of unhybridized p orbitals. And let me point out that these p's are 90 degrees to the formation of the sigma bond. I think I drew a theta here, didn't I? I think a sigma would be more like that. You get the idea. All right, so anyway, those P's are at 90 degrees to the sigma. And you can see they're starting to blend together here. That's what those dotted lines, those wavy lines are showing you. They're beginning to merge. Now there's two lobes to a p orbital. There's one up and there's one down. So eventually they're going to lay down side to side on top of the sigma bond. And then also these two lobes down here are going to lay down. So eventually you're going to make this pi bond, and it looks kind of weird because there's a top and a bottom to it. You have a region above and below the plane of the sigma bond. So if you have an electron here and an electron here, when they overlap, those electrons could be right here. But they don't have to stay there. Those electrons could end up being down here. They have the ability, almost like teleportation, and I'm not kidding, to just pop out of existence here and pop into existence down here. They don't pass through this area. That's the sigma area, but they blink in, blink out, almost like an X-Men or some superhero. Okay, so that's the pi bond. It's the region up here and up here. These two electrons will be either in the top or the bottom, not both. There's only two electrons here. So what is the consequence? Why do we care? What do these pi bonds do to us? Well, if I have pi bonds added to the sigma, I end up having more than one connection between two atoms. So pi bonds will add strength. A single bond is always going to be weaker than a double bond. And a double bond will always be weaker than a triple bond. The more pi's you add on, the stronger the bond gets. As a consequence, as you add more of these pi bonds and strengthen the connection, the bond lengths get shorter. Single bond carbon is going to be longer than C triple bonded to carbon. And we're not, and it's pretty noticeable. I mean, we're talking about a big difference here. Another thing is that the pi bonds add rigidity. So you can no longer rotate around the sigma bond. You can't spin. And that inflexibility is important because as molecules react and they have to collide and torsional strains and things like that, becomes very important for the energetics and the kinetics of the reaction. That's a little bit above the scope of what we're doing right now. So instead, what I want to do, just really the only thing we need to be able to do with this is just kind of count our sigmas and pi. Conceptually, I need you to know this. I need you to know what the consequence of adding pi bonds, doubles and triple bonds. What do they do for the bonding? And that's add strength, which is bond energy. They shorten the bond length and they prevent rotation. So now I'm going to draw you a picture of a molecule, and we're going to try to pick out how many sigma and pi bonds there are. All right, here is one example of a molecule I just made up. I don't know the name of it or anything, but let's go through and count first the sigma bonds, and then we'll count the pi bonds. Every single bond that you see is made from the overlap end to end, so that's a sigma. So we have here 1, 2, 3, 4, 5, 6, and then there's a sigma in every multiple bond. So that is a grand total of 1, 2, 3, 4, 5, 6, 7, 8 sigma bonds. And now we go through and do pi's. Every additional one has a pi. So I see here 2 pi bonds. Let's do another. Here's another crazy molecule. Let's go through and count our sigmas. I see one here. So 1, there's one there, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14. So unless I missed one, there's 14. Now if we go through and do our pi's, This time there's a pi here, but this is a triple bond, so there's actually 2 pi's. And then we have a double bond here, so that's the third. 4, 5. And I believe that's all. So there are 5. Notice that I did not count these lone pairs, even though they were drawn in. Lone pairs do not occupy sigma or pi bonds. They're just unbonded. But they can be in hybridized orbitals. They're just not, like for example, this sulfur right here is sp3 hybridized, but it has only formed 2 sigma bonds. All right, I hope that makes sense. We'll have a little practice on this, probably a warm-up for a day or two, and then you'll see questions like this on the test.